Okay, everybody, this is section 4.8, applications and models. So we're going to be looking at solving real-life problems that involve right triangles, which we've already laid a foundation for somewhat, but we're going to deal more with the angle measurements this time too. And then also talking about how you might set up and solve problems in using directional bearings. So being able to actually use angle measurements to help thinking more about things like vectors in physics or directional headings when you're setting up and solving problems. Day 2, we'll get into the solving harmonic motion questions, the bottom part there. So we're going to be looking at the top two for today on this day 1. So you'll see a lot of familiar things today, and then one new idea. So we'll talk about one new thing as well. So let's take a look at some applications just to kind of get thinking about these SOHCAHTOA triangles again. So we're going to start right in with an application and see if we can draw a picture that will help describe the situation that we're looking at. So remember, when we're trying to do right triangles, we're trying to see if we can use what we have and what we're trying to solve for, what trig ratio best represents that situation. So I'm going to ask that you try to go ahead and draw what this is saying. So it says a ladder leaning against a house reaches 24 feet up the side of the house. The ladder makes a 60-degree angle with the ground. How far is the base of the ladder from the house? Round your answer to 2 decimal places. So I'm going to go ahead and let you pause here. So if you want to pause, go ahead and try to draw the picture, and then we're going to check in and see how that looks. All right, so if we talk about a house, so we have our house, and then we have a ladder leaning up against the house. It says that the ladder reaches 24 feet up the side of the house. So that means the distance along the side of the house is that 24 feet. And the ladder is making a 60-degree angle with the ground. And we're making the assumption here then that the right angle is right at the house to the ground. Hopefully it is, otherwise your house is a little wonky. What you want to try to figure out then is how far is the base of the ladder from the house. So you're looking for that distance right there. So I'll assign a variable to it so we can talk about it. So that side is adjacent to the 60-degree angle. The 24 is the side that is all the way across, so opposite. So which trig ratio uses opposite and adjacent? That would be tangent. So the tangent of 60 degrees would be equal to, think about what ratio that would be, opposite over adjacent. All right, so I want you to think for a moment how you would solve something like that. If you have a variable in the denominator, how do you get it out of the denominator? Well, we need to multiply both sides by the x. So we have x times the tangent of 60 degrees would be equal to 24, and then we go ahead and divide by the tangent of 60. Now, if you remember what the tangent of 60 is, root 3. You can type that in a little bit faster. Otherwise, you're going to do that on your calculator. And let's just be clear here. Look at your little thought bubble over here. What mode should your calculator be in? Well, we have a degree measure, so make sure you're in degrees. So just be careful when you do that calculation. So it looks like, to me, looks like I'm getting about 13 point. It says round your answer to 2 decimal places, so 8.6, and that would be in feet. So the whole idea is we can set up a triangle to help us solve for the missing parts, the things that we need to do. So we could actually figure out the length of the ladder now too. That would be finding the hypotenuse. We could set up a SOHCAHTOA ratio to do that, or even Pythagorean theorem. So we have lots of options. All right, let's take a look at another one. We're going to add a few. So if you can take a moment, pause, go ahead and pause the video if you need to, so you can write down the information. This is a checkpoint, so there is a video that we'll go with too if you need to just watch this particular question again on larsonprecalc.com. So here's the scenario. It says a point 65 feet from the base of a church. The angles of elevation to the bottom and the top of the steeple are 35 degrees and 43 respectively. So that means the angle of elevation to the bottom of the steeple, 35, and then to the top of the steeple, 43. So bigger angle to the top of the steeple, you have to look up higher to see that. Find the height of the steeple. All right, so once again, we're going to try to describe this with some sort of a picture. So again, go ahead and pause if you need to write down the information and see if you can draw what this looks like. So go ahead and pause, and then we'll come back together here. So we have a church of some kind here, and then we have the steeple at the top, and then we're talking about the angle of elevation to the base of the steeple is 35 degrees, and then the angle of elevation to the top of the steeple, so that whole angle is 43 degrees. All right, and they want us to figure out the height of the steeple. So we just want the height of the steeple. I'm going to go ahead and drop this perpendicular all the way down though so we can see these. We actually have two different triangles going on in this picture. We have the just to the base of the steeple, so that's our red triangle. And then we have the all the way to the top of the steeple, which would be this green one. And what we're trying to figure out is just the height of the steeple itself, which is this distance right here. So that's the steeple. All right, so I want you to have a quick conversation with your partner. How do you think that you would calculate the height of the steeple if we could figure out some dimensions in here? So we know one more number, that this person who's measuring those angles of elevation, the happy little person, the surveyor there, is 65 feet from the base of the church. So we know that that distance is 65. So go ahead, pause, talk it through. How do you think you'd find the height of the steeple? What ideas do you have? Then we'll come back together. All right, well, hopefully we've talked about the fact that in that green triangle, we could figure out the entire height, steeple and church together. So we could figure out that distance. It's the side that is opposite, and you know the adjacent. And then in the red triangle, we could do the same thing. We know the side that's opposite, or we want to find the side that's opposite, and we know the adjacent. And that's just the height of the church. So if I know the height of the church with the steeple, and then just the height of the church, to find the steeple, I just have to find the difference between those two numbers. So I'm going to kind of color code here. Let's take a look, and I'm going to label. So the opposite side for the green triangle, I'm just going to go ahead and call that Y, I think. And then for the red triangle, I'm going to go ahead and call that opposite side X, just so we can keep things straight here. So oopsie daisy. So in my green triangle then, that's the 43-degree angle. We're going to be using tangent because, again, it's opposite over adjacent. So tangent of 43 degrees would be equal to Y over 65, opposite over adjacent. In the red triangle, that would be the tangent of 35 degrees is equal to X over 65. So we have two triangles, but the nice thing about this is each of these can be solved for its variable. So go ahead and take a second to type that in. So 65 times the tangent of 43 degrees, and then 65 times the tangent of 35 degrees. Once you have each of those values, then we can find out the height of the steeple by finding the difference. All right, so for the first one, for my Y value, looks like I got 60.61. And for the smaller, the shorter one, just the church, that would be the 45.51. So this is just the church, and that's the church plus the steeple. So if you want to figure out just the steeple now, you just have to find the difference. So the height of the steeple would be about, looks like, 15.1 feet. So when we think about using SOHCAHTOA triangles, again, we're just always looking for how can we make a right triangle to help us solve this situation? Is there a way that we can use what we have and what we want to find with a right triangle? Okay, so we're going to try one more here and see if we can figure out what's happening in this one. So we're going to look at an airplane one again. So again, this is a checkpoint, so there is a Larson pre-calc video for just this question. Let's see if we can draw this picture. So again, pause the video once you've had a chance to read through it here and make sure that you can draw the picture, and then we'll come back together. So I will read it to you here first. From the time a small airplane is 100 feet high and 1,600 ground feet from its landing runway, the plane descends in a straight line to the runway. Determine the angle of descent in degrees of the plane. All right, so we might need to clarify a few things, but I just want you to think about what ground feet might mean. Common sense here, feet from on the ground. So basically you're talking about that horizontal distance along the ground. So we have an airplane, sort of an airplane. All right, it's not that bad, I guess. So it is 100 feet high. So the distance elevation is 100 feet. Ground feet from the airport, from the end of the runway, is 1,600, so feet along the ground. So the airport's down here, the runway's down here. They're going to make a straight descent to the airport. So that's their flight path. So they're actually flying along that red line. All right, so what do you suppose the angle of descent might be? Okay, well, think about the angle of depression. So if we think about if they continue to fly straight ahead, that would be the horizon for them. Its angle of descent then is the same as the angle of depression. It would be this angle on the outside. So this would be the angle of descent. All right, so let's see if we can figure out what that would be. So the angle of descent is what we're trying to solve for. Now I know that's not inside the triangle, but remember the flight path, that dotted line, and the ground are actually parallel. So the angle down here that the airport makes with the ground is going to be congruent to the angle on the outside. So this is really theta as well. So when we're looking at these, we can definitely look inside the triangle then. Those are, it's a transversal, so those parallel lines, those would be congruent angles. It might be easier for you to think of it inside the triangle. We're assuming our right angle is there. So let's see what we know. We know the opposite side, and we know the adjacent side. And what we'd be trying to find here is we'd be trying to look for that angle measurement. So let's see if we can do that. So tangent of the angle, so opposite over adjacent, would be equal to 100 over 1600. Okay, well, we haven't really addressed this before for a while anyway, but we're trying to solve for the angle measurement, right? We want to know what theta is. What is that angle of descent? So we're supposed to undo tangent. So here's where we're going to use that inverse information that we were talking about earlier in the chapter. If you want to undo tangent, we do inverse tangent on each side. And I know a lot of you don't show this on each side, but that's really what you're doing. We're doing the opposite operation to undo tangent to see what that angle is. So tangent of the inverse tangent, that's going to leave us with theta. And then again, we just need to type this into our calculator. Again, remember you're in degrees on your calculator. So when we do inverse tangent there, looks like we get about a little over 3.5 degrees. So 3.58 degrees would be its angle of descent. Now remember, you really don't want a big angle of descent, right? When we're talking about an airplane going down to the airport, we like a nice gentle angle. No 70-degree angles of descent here. Nice and easy right into the runway. So you can actually find angle measurements as well, which sort of brings us to our last point before we do our new piece here. If you're going to be asked to solve a triangle, that means sometimes you have to find angle measurements too. So it's not just all about side lengths, it's about angles as well. So remember when it says solve the triangle, what they're asking you to do is find any missing pieces that you have. So you're going to find all angles and side lengths that you don't already know. So we're going to go through and find the missing pieces. So in this one, kind of nice, we already know angle A is 20 degrees. So the only other angle I need to find is angle B. Well, if it's a right triangle, and we know one of the acute angles already, how would you find angle B? Well, we're just going to subtract from 90 degrees, right? Those two other acute angles have to add to 90, so that angle B would be 70 degrees. So if you know one of the angles already, it's pretty nice. Otherwise, you can use a trig ratio like we did in the last one. All right, we only know side little b, remember across the triangle from the vertex that's labeled angle B is going to be our side B. So when we label this, I would say that little b is 15, which means we don't know side C, which is the hypotenuse, and we don't know little a, which is across from the 20. But let's see if we can use a trig ratio to help us solve for that. So say we just use the 15, because that's really the only side length that we have. And we can just use the 20, I guess, because that's the one we were given. So in that situation, the 15 is the adjacent side. The A would be the opposite side. So which trig ratio uses opposite and adjacent? Well, that's tangent. So we'd say the tangent of 20 degrees would be A over 15. And I could solve. So multiply by 15 times the tangent of 20, and I can do that calculation. So 15 times the tangent of 20 would give us our value for that first part, which is about, looks like 5 point something, 5.46-ish. Now, remember, if you wanted to use the 70-degree angle, you totally could have. For 70, it would have been opposite would have been 15, and then the adjacent would have been the A. So you could have said tangent of 70 equals 15 over A. You would have had to divide then, so 15 divided by the tangent of 70, and you should get the exact same answer. So realize there's always different ways to do these depending on which angle you're using. All right, so we just figured out we have little a, so 5.46. Now we want to find side C. That's the only thing that we have left. Some people might say, hey, well, I could use Pythagorean theorem. Sure, you could. The problem is you're going to be using a rounded number, which is going to make your answer even more off than what it would have been. So let's go back and use a trig ratio. So I'm going to go back to the 20 degrees and the the 15, what I was given. Given information is always the best bet. It's exact. So let's take a look at that. So we have adjacent, the C is the hypotenuse. Which trig ratio uses adjacent and hypotenuse? Well, that'd be cosine. So we've got cosine of 20 would be equal to 15 over C, and then I'm going to solve. So again, remember, I'm going to multiply by the C, get that out of the denominator, and then we're going to divide. So divide by cosine of 20. Again, if you would rather use the 70-degree angle, totally fine. You'd just be using the sine function then. So C would be equal to whatever 15 divided by the cosine of 20 is, which is about almost 16, looks like 15.96. Now let's talk about reasonableness here. So let's check in on reasonable. Do you find those answers reasonable? And what about them makes it reasonable? Well, which side is across from the 20? The 5.46, that's the smallest side. It's across from the smallest angle. That's reasonable. Look at your hypotenuse, 15.96. Biggest length? Yeah, it should be. It's the hypotenuse. It's always going to be the longest leg. So we can use what we know about SOHCAHTOA to help us solve all sorts of different things, angles and side lengths, which brings us to a really cool application. So for the last couple minutes here, we're going to talk about being able to actually write like bearings and headings. So if we're going to talk about, say, navigation or things like that, and we want to try to use what we know about trigonometry to help us in those settings, we need to all have a way to describe how we go in different locations or get different directions. So we're all kind of doing that in a uniform way. So they're called directional bearings. So in surveying and navigation, a directional bearing measures this, and this is the important part. We all have to do it the same way so it's standardized. The acute angle, okay, so a less than 90, that a path or line of sight, so like the direction you're heading, makes with a fixed north-south line. So you are always doing your directional headings based off of how far away you are from the north-south line. Always north-south. So that's really important because if you're doing it from east-west, then you're going to get different angles than we do. So you got to make sure we're always doing it, we're standardizing. So we know we're always talking about our path from north-south. So I'm going to go ahead and do this one that they're going to ask just so you understand how they're going to write them. So this is a bearing. It says N 70 degrees E, which looks like, well, how are you going to say that? You don't say it how I just said it. Actually, you would read this as 70 degrees east of north. So remember, we're always comparing to the north-south line. So this means we're on the north side, meaning above where the x-axis is, and the E means you went east of that, so to the right of that, and the 70 degrees tells you how far you went. So you actually kind of start at the middle and then the end and then the front when you actually read it. So 70 degrees east of north. Okay, what does that mean? So I didn't go straight north. I went 70 degrees towards the east of north. So my path or my directional heading was that. Now, most of us, if we were reading a map, we would be saying, oh, I headed to the northeast. So if you hear someone say, I'm going northeast, yep, that's what that means, but that's directionally how we would say it. So 70 degrees east of north, yep, that's in the northeasterly direction. So that's just the technical way of being able to describe that. So we're going to practice a couple of those, make sure that we're okay, always from the north-south line. All right, so let's take a look at the example 2. It says, write the bearing for the path shown in the diagram below. They can put the angle measurements wherever they want. This one is telling you how far it is from the east-west line, which is great. That's good information. What we need to know, though, is how far is it from the north-south line. So if it's 30 degrees away from there, we need to do 90 minus 30, right, to figure out what it is here. So that's 60 degrees. All right, now the direction that it's pointing is this. So I think most people would look at that and say, oh, it looks like we're going to the southwest. But how are we going to say that? Well, first of all, it's below the x-axis, so we're heading in the south direction. So south, first of all, it's below. Now, which side of the y-axis are we on? Well, we're heading towards the west. And then how far? We're 60 degrees away from that north-south line. So it would be 60 degrees, always from the north-south line. So the way I would say this, I would say that this is 60 degrees west of south. So when I'm describing that heading, so I'm going below, so my heading is in that direction, so I'm on the south direction, and I'm going 60 degrees west of that. So I didn't go due south, straight down would be what they would call due. So due south would be straight down. I'm going 60 degrees to the west of that. So that would be 60 degrees west of south. So how we think of it, I know it's kind of seems a little bit backwards, but that's how you would say it. All right, so let's do a couple where you're going to draw these. So you can pause the video to try each of these and then take a look at the answers just to make sure you're okay. So we're going to take a peek and see if this makes sense. So when I look at this first one, I'll read it to you and then I'm going to have you pause the video and then see if you can figure out what that means. So how I would say that is 35 degrees east of south. Okay, so pause the video and give it a try. Okay, so 35 degrees east of south. So I'm going to be heading in the south direction, so it's going to be below the x-axis, and I'm going to be going towards the east by 35 degrees. So my directional heading coming from the origin then would be 35 degrees east of south. So it'd be down in quadrant 4. So in the south direction, and I went towards the east, 35 degrees. Okay, let's try the next one. So 80 degrees west of north. So go ahead and pause the video, give that one a whirl. So 80 degrees west of north. Okay, so instead of heading straight north, I went to the west some and I went 80 degrees to the west. So now what's critical to have in your picture is you need to have the direction arrow so you know how far away it is, and you need to have the actual flight or sight path that you're going to have in there. So having both of those pieces is really important. So the arrow that's showing your path and also the direction that you are, the distance you are from that north-south line. Okay, let's try one more here and see if we're okay on the headings. This is part of how you draw navigational pictures and charts and things, so we need to understand how to read them, right, before we can draw the pictures. All right, so write the bearing for this one. So I'm giving you a picture. I want to see if you can describe it. So go ahead, pause the video, give it a whirl. All right, so first of all, we're heading in the north direction. So this is going to be north. We're going to the west side. So we're definitely west of north. And by how far? Well, it looks like they went 60 degrees away from that. So how you would say this would be, see if you can say it, 60 degrees west of north. All right, and those are directional bearings, so we can be able to talk through and draw the pictures that we would need to make when we do navigation charts and directions. So I have the assignment for this day 1. We'll open up the Smart Notes so you can see all of the questions, so you have everything, because some of these are a little bit long because when they're written out to look at the actual, the actual equations and things or the pictures. So you can take pictures or pause. There's one about the length of something. There's a distance for a lighthouse there. There's another looking at 2 different sight lines from an airplane. So there's that one. We've got an angle of elevation on a cell phone tower. And then we got a fun, look at the water slide. That's exciting. So we got a water slide. And then the very last ones here, we have a navigation and they have a bearing for you to do. So that's our day 1 assignment, and hopefully we're going to be okay with solving equations in SOHCAHTOA triangles and then navigational bearings.